In this video, our goal is to learn how to identify and graph a discrete probability distribution. So, to get us started, let's consider an example. Suppose you conduct the statistical experiment of tossing a coin 2 times, and you're required first to write out the sample space of the experiment. Of course, every experiment in statistics definitely has a set of possible outcomes, which is called the sample space. So, if this is the coin, the first time it was tossed, you can either end up with a head or a tail. If on the first toss it ends up being a head, then on the second toss it could be followed by either a head or a tail. The same argument can be made for if on the first toss you got a tail, it could be followed by either a head or a tail. So the sample space is head-head or head-tail or tail-head or tail-tail. These are the set of all possible outcomes, which is otherwise called the sample space of this experiment. So the sample space will be given as S with the points head-head, head-tail, tail-head, and tail-tail. Question B. In this example, we shall let X be the number of tails in each of the points in the sample space in part A. What are the possible distinct values of X? Or, since X represents the number of tails in each of the points in the sample space, what are the possible distinct values of X also means what are the possible distinct number of tails. Let us see. So if we do a one-to-one observation, so if we're counting the number of X, number of tails in the points in the sample space, we have how many tails do we have here? 0. How many tails do we have here? 1. How many tails do we have here? 1. And as you might reckon, 2. The question here, so we have listed out the possible distinct values of X, but in particular, the possible distinct values of X are actually 0, 1, or 2. So that question is answered. In other words, in our final submission, the possible distinct values of X or possible number of tails are either 0, 1, or 2. Then based on this, we proceed to question C. We are required to compute the probabilities of obtaining each of the possible values of X and summarize your result as a table. Sure, these are the possible values of X. It could be 0, 1, or 2. Then you have the corresponding probabilities of possible values of X. For example, how many times does 0 occur? This will be 1 out of 4. How many times does 2 occur? Does 1 occur? Twice out of 4 possibilities. And for 2, it will be 1 out of 4. As you might observe, this might remind you of a probability model. Why? Each of the probabilities is a number between 0 and 1, and the sum total of all the probabilities is equal to 1. And that naturally leads us to question D. Why is the table obtained in C above a discrete probability distribution? Here are the reasons. Reason 1. Each probability is a number between 0 and 1 inclusive. Reason 2. The sum of all the probabilities, which is 1 over 4 plus 2 over 4 plus 1 over 4 is equal to 4 out of 4 or 1. Because these two properties are satisfied, we can say that this table is a discrete probability distribution or a discrete probability model. So why did we take this question? It is because naturally it lends us or leads us into the rules for what constitutes a discrete probability distribution or model. As long as we have a table, a formula, or a picture where there is a depiction that the sum of all the probabilities is equal to 1, and each probability is a number between 0 and 1, inclusive, we do have what is called a discrete probability distribution model. We take another example to further emphasize what we are learning here. In this example, we are told that a child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X here denote the number of times per week a newborn baby's crying wakes its mother after midnight. For this example, the possible number of times X that a newborn baby's crying wakes its mother after midnight is 0, 1, 2, 3, 4, or 5. And, naturally, P of X will be the probability that X takes on any of its possible values. So we have here provided with the table and the possible number of times that has been observed that a newborn baby's crying wakes its mother after midnight. How often does it occur that a newborn baby wakes its mother 0 times? It is twice out of 50 observations. What about once? 11 out of 50 observations. You get the idea. The same interpretation applies to each of the possible values of X and the respective probabilities. And that leads us to the question. Is this a discrete probability distribution? Why or why not? Well, I need to check again if each probability is a number between 0 and 1, and then check if the sum of the probabilities is 1. That I can do. First of all, 2 out of 50 lies between 0 out of 50 and 50 out of 50. 11 out of 50 also lies between 0 out of 50 and 50 out of 50. If you check each and every other probability value, they all satisfy this requirement, which means check. Each probability is actually a number between 0 and 1 inclusive. Then, the other condition to check is if the sum of the probabilities is equal to 1. So, what do I need to do? I need to add up all of the probabilities. What I might quickly observe is that each denominator here is 50 in this case. So I might not need a calculator. 2 plus 11, 13. 13 plus 23 is 36. 36 plus 9 is 45. 45 plus 4 is 49. 49 plus 1 is 50 out of 50. So the sum of the probabilities is 50 out of 50, which is 1. In other words, condition 2 checks out. The sum of the probabilities of all the probabilities is equal to 1. Then we can say that yes, this table is a discrete probability distribution. The reasons for which this table constitutes a discrete probability distribution model are given. Reason 1, as we said earlier, is documented here, and reason 2 is also documented in writing here. So, the probability distribution of a discrete random variable X will provide first the possible values of the random variable, as you can see in this table. These are the possible values of the random variable and their corresponding probabilities. 1, 2, 3, 4, 5, 6. So, a probability distribution model can be in the form of a table, as we saw in this example. Sometimes it can be given by graphs or even a mathematical formulae. With that said, let's proceed to the next example. In this example, we're told that suppose Nancy has classes 3 days a week. So, Nancy has to attend classes 3 days a week. She attends classes, however, 3 days a week, only 80% of the time. At other times, she attends classes 2 days a week, 15% of the time, one day, 4% of the time, and no days, 1% of the time. What would our X be? It would be the number of days Nancy attends classes weekly. That is the variable of interest here. What possible values does X take? Take note, X represents the possible number of days Nancy attends classes weekly. Within the context of what we are learning here, she can attend classes either 3 days a week, 2 days a week, 1 day a week, or 0 days. So our X here, the number of days she attends classes a week, could take on the value 0, 1, 2, or 3, based on the context of the problem. So, question C. Suppose 1 week is randomly chosen. Construct a probability distribution table, also called a PDF table. Well, first step, I'll write 0, 1, 2, 3. Why is that? Because we just learned earlier that a probability distribution for a discrete random variable will first provide all the possible values of the random variable and then followed by their corresponding probabilities. So I have 0, 1, 2, 3. So as it stands, I need to compute the respective probabilities. To do that, take note that she attends classes no days or 0 days 1% of the time. So this is 1%, 0.01. And then 1 day is 4% of the time. Okay, that is 0.04. 2 days, 15% of the time, same as 0.15. And 3 days, 80% of the time. So that is 0.80. Looking closely at this table, we can see all the possible number of times Nancy attends classes weekly. We can also see the corresponding frequency or probabilities of the different number of times she attends weekly. We can say we have constructed a probability distribution table. The next example tells us to determine the required value of the missing probability to make the distribution a discrete probability distribution. In other words, already we have provided the possible values and an attempt has been made to provide the probabilities corresponding to each of those possible values of x. However, something stands out. There is a missing value with the question mark. How can we solve for the missing question mark here? What we might observe is that a probability distribution should document the different values and the individual probabilities. Each individual probability must be a number between 0 and 1, and the sum of all probabilities must equal to, yes, you guessed it right, 1. So you have 0.16. So looking back at my table here, I should have 0.16 plus question mark, the unknown. Let me call that x as a placeholder, plus 0.38 plus 0.22 plus 0.38 plus 0.22. This must be equal to 1. On the left-hand side, I can see numbers 0.16, 0.138, and 0.22. How about I collect like terms by adding up all of these numbers? I will have 0.76 plus x is equal to 1. Subtracting 0.76 from both sides, I will have x is equal to 0.24. So, with that said, we have an answer for the missing question mark. X represents question mark, so x is question mark equals 0.24. This is our answer that makes this table a discrete probability distribution? Having completed that question, we proceed to the next example. In the following probability distribution, the random variable x represents the number of activities a parent of a K to 5th grade student is involved in. It could be 0, it could be 1, it could be 2, it could be 3, it could be 4, with the frequency of its occurrence or the probabilities, the respective probabilities precisely. We'll use this information to complete parts A through F below. First, we're to verify that this is a discrete probability distribution. What do you think will be our first step here? We'll need to check if each, emphasis on the word each, if each probability is a number between 0 and 1. Do you think that checks out? I think it does. So we can write that this way. Each probability is a number between 0 and 1. And second condition to check will be to add up all of the probabilities as a combined whole. So 0.448 plus the next sequence of numbers. I'm going to write that down. Here I have written down all of the probabilities, and if you check it out, this should give you 1. Since these two conditions are met, we can say that this table constitutes a discrete probability distribution. The next step will be to graph the discrete probability distribution, or choose the correct graph below. In order to graph this probability distribution, I will add on into StatCrunch. So I have StatCrunch open here. I have the possible values of x and the probabilities of x. So in order to get started, I will go over to statistics or stats, go to calculators, and I'll scroll down to custom. Click on that. I'm going to select my values are stored in X, as you can see, and the weights are stored in the probabilities of X. So I'm going to go ahead and do that and hit the compute button. And there you are. So you can see that for 0, you have this, for 1, for 2, and for 3, and for 4. I'm also provided the mean and the standard deviation of this random variable. We will get to that in a little bit. So in particular, I can see that this looks approximately right skewed. At this point, I will add on back to my workbook and I'll look at the options I have. The first one, does it look anything like this? I would argue I see the tall, and then there's a ridge, and then a rise, and then a fall. It appears that the first one, the fall, the rise, then the fall, that is the one that meets the description of the graph we just drew. So my graph here would definitely be this first one. Then the next question is, what is the probability that a randomly selected student has a parent involved in 3 activities? Well, our X in this case was the different number of number of activities parents were involved in, and the corresponding probability for when X is 3 is 0.103. With that question answered, we proceed to question D. What is the probability that a randomly selected student has a parent involved in 3 or 4 activities? Well, 3 or 4, that will be either this much or this much. So this interprets to probability that the number of parent activities is either 3 or 4. This is the same as probability of x equals to 3 plus probability of x equals to 4 combined. And that will be 0.103 plus 0.071, which gives 0.174. And that brings us to the end of that question.